Let's jump right into this explainer. Today, we're unpacking the absolutely wild microscopic engineering that's taking sleek, everyday augmented reality glasses straight from sci-fi into reality. Now, if you close your eyes and picture a hyper-realistic cinematic close-up of futuristic AR glasses resting on someone's face, you're probably imagining all this glowing, impossibly complex tech, right? But the reality, the hardware actually required to make this work out in the wild has to be practically invisible. So we are going to look at the microscopic sensors and nanoscale manufacturing that put this tech right onto your retinas. Seriously, put yourself in this POV for a second. You walk out of a pitch black room directly into intense, blinding sunlight. Now, in older headsets, your digital world would instantly lag, glitch out, or just completely disappear. But with the tech we're exploring today, your holographic retinal display stays ultra sharp, zero latency, the environment shifts abruptly, but the projection is perfectly robust and completely uninterrupted. So how on earth is that physically possible when traditional cameras literally wash out in the sun? Well, to understand this seamless, sci-fi-like experience, we first need to tackle the eye tracking bottleneck, namely why current tech totally fails in the sun. When you compare the old guard to the new frontier, the difference is night and day. Traditional video oculography, or VOG, is basically the state-of-the-art for most mobile eye tracking right now. It uses bulky camera sensors to track your pupil in a 2D image, usually with the help of infrared LEDs. But here's the catch. It is incredibly power-hungry because analyzing all those images takes serious computational muscle. And worse, VOG cameras have a super limited dynamic range. When you step into that blinding sunlight we just talked about, the camera gets completely flooded with light and loses your eye entirely. Enter laser feedback interferometry, or LFI. This is the game changer. Invisible integration, incredibly low power consumption, and it is highly robust to those extreme changes in ambient light. And that brings us to laser feedback interferometry. This is honestly the invisible hero of gaze tracking, replacing those bulky, power-hungry cameras with something way more elegant. Hidden away inside these sleek, modern frames is a tiny vertical cavity surface-emitting laser, or VCEL for short. If you were to take an extreme macro shot of the inside of the lens, you wouldn't see a camera staring back at you. Nope. Instead, you'd find a highly integrated microscopic eye tracking sensor array. The LFI sensor is actually built right into the RGB module, meaning it shares the exact same optical path as visible light. Then, a holographic optical element acts as a wavelength selective mirror, bouncing a scanned pattern of faint, elegant near-infrared laser beams directly onto the surface of your eye. And the best part? It's completely invisible to the user. Okay, so how does this actually build a robust signal? Well, it all comes down to the physics of the coupled cavity model. Here's how it works. Step 1, the laser emits that faint near-infrared light. Step 2, the light hits your eye, whether it's bouncing off the sclera, the iris, or the retina, and it scatters back. And step 3, which is the really clever part, this backscattered light is injected directly back into the laser cavity itself. A tiny photodiode integrated into the back mirror instantly monitors the optical power changes inside that cavity. Because it's measuring changes in the laser's own feedback path instead of snapping a photo, it tracks the rapid, darting movements of your pupil with zero latency. And it is completely unaffected by how bright the sun is shining outside. So now that we have this incredibly robust, hyper-fast eye tracking, how do we actually use it to project vivid holograms without instantly draining the battery of your smart glasses? That brings us to our next piece of the puzzle. The software trick, better known as foveated rendering. Foveated rendering is an absolutely ingenious software trick that basically piggybacks on human biology. You see, we can only perceive the absolute highest resolution at the very dead center of our field of view. We actually detect way fewer details and colors in our peripheral vision. So rendering a massive, highly detailed digital landscape across your entire periphery, that's basically just throwing away processing power, because your eye physically can't see those details anyway. By feeding instantaneous data from the LFI sensor into the system, the AR software drops the resolution in your periphery, drastically cutting down the computational resources needed to draw the image. The crucial takeaway here is that you end up with a floating, holographic retinal projection that adjusts seamlessly in real time. By rendering an ultra-sharp 8K resolution exactly in your direct line of sight, kind of like a cinematic shallow depth of field effect, and dynamically blurring the periphery, the system saves massive amounts of battery life and compute power. And because that LFI eye tracking is so blindingly fast, the 8K sweet spot moves exactly where your pupil darts. You remain completely oblivious to the trick. To you, the world just looks perfect all the time. All of this sounds amazing, but how do we actually build these tiny, multi-depth optical components and microsensors in the first place? Let's get into manufacturing at the nanoscale, or as I like to think of it, building the impossible. Turning this sci-fi concept into a manufacturing reality actually relies on a breakthrough tech that's currently celebrating its 30th anniversary. It's called nano-imprint lithography, or NIL. First introduced way back in 1995, this technology fundamentally shook up everything we thought we knew about mechanical patterning. Fast forward to today, and it is the absolute cornerstone for crafting advanced microchips, flat optics, and yep, the intricate lenses inside modern AR glasses. What makes nano-imprint lithography so fascinating is how it stepped up as an alternative to insanely expensive extreme ultraviolet lithography for deep nanoscale electronics. NIL literally uses a patterned hard mold to mechanically press into a thin polymer resist. Just by molding the material, it can reliably stamp out features smaller than 10 nanometers. To put that into perspective, that is mind-bogglingly tiny. But more importantly for augmented reality, it allows for direct 3D patterning. This means it can create multi-depth, slanted nanostructures, often sitting at precise 25-degree angles that continuously split and route light. That level of extreme precision is absolutely critical for manufacturing the complex waveguides and microscopic displays hidden inside your headset. So, we've covered the microscopic sensors, the software tricks, and the nanoscale manufacturing. Let's bring it all together and look at the future of wearables, and more importantly, what this actually means for you. When you combine all these elements, we hit the holy grail, a genuinely seamless AR experience. We start with microdisplays. These are electronic panels smaller than 2 inches diagonally, pushing out high-res images designed to be viewed through magnifying optical elements. Pair those displays with LFI sensors for ambient light robustness, and you get absolutely zero glitching when you walk outside into the bright sun. Then, layer in foveated rendering to keep the power consumption low enough for everyday, all-day wearability. And finally, because the eye tracking is so highly accurate with basically zero latency, the digital world matches your actual biological movements perfectly. That is a huge deal because it helps avoid motion sickness entirely. All of this leaves us with a truly mind-bending question to wrap up this explainer. How is your daily life going to change when your screens are no longer just rigid devices you carry around in your pocket, but ultra-sharp, real-time holograms projected directly onto your retinas? When the digital and physical worlds just blend perfectly, no matter the lighting, all powered by microscopic tech you can't even see. It is a wild, fascinating future. And thanks to breakthroughs in nanoscale manufacturing and laser interferometry, it's a future that's being built right under our noses. Thanks for hanging out with me for this explainer, and definitely keep your eyes open for what's next.